Improper integrals. That is our concern today. What makes them so improper? They are improper essentially because they've got an infinite problem going on with them. Type 1, you can obviously see the infinity problem. Dink, dink, or double dink, dink. The type 2 is where you actually have a vertical asymptote in the domain. Now, this labels type 2 as discontinuous integrands. And just to clarify, integrands are the function in between the s integral symbol and the dx, or the differential. Back in AB calculus, you did deal with some discontinuous integrands. You dealt with piecewise functions. With a piecewise function, the graph might go la-di-da-di jump, la-di-da-di-da. And I'm just going to emphasize 1 point's defined, 1 point is not defined. When that was what you were dealing with, you could integrate it. You just needed to take where it split its domain, I'll call it C, and then go from A to B and solve 2 separate integrals. We are not dealing with jump discontinuities this time. We are dealing with vertical asymptote discontinuities, and that's a whole new ballgame. Now, everything we're going to do here, you've done before. It's just we're bringing 2 ideas together. We're bringing together how to solve limits with how to solve integrals together into one problem. The first step is rewriting as a limit. When you rewrite as a limit, you're going to take where the infinity problem is located, replace it with a letter of your choosing, and have that letter approach that infinity issue. When I look at, and by the way, number 18 is actually in the, it's not an assigned homework problem, but I thought it would be good to refer to some of the problems within the homework section. This one, the issue is at the other end. Just pick a variable and then the limit as that variable approaches negative infinity in that case. Now, for the discontinuities, these 2 examples, 28 and 30, are endpoint discontinuities. If you look at the integrand, x equals 3 makes that denominator 0. That's a problem. So that has a right endpoint discontinuity. You will replace that right endpoint number with a variable. And very important, you're only dealing with one side. So if I look at what an interval between 2 and 3 looks like, I have to be approaching 3 from the left side. So make sure that you know the proper limit to set up. In fact, every limit that you solve, if you really properly solve it, you only solve one-sided limit at a time. Often we kind of skip and see both sides do the same thing and forego the details. But understand that every time you're solving a limit, you are only looking at one direction being headed toward. When we're dealing with limits as we approach infinity, we are looking at just one particular direction being headed toward. Now, for problem 30, 6 makes the denominator equal to 0. It has to be replaced with a variable of your choosing. If it is the left endpoint, where you have a discontinuity, realize you are approaching from the right side. Now, the problems numbered 22 and 34. 22 has a problem of having two separate infinities. We can only deal with one very specific direction of movement of a limit. We have to split this interval up into two intervals. Let me zoom in on that a little bit. Now, you can choose any real number to split it up at. It's totally up to you. But if it were up to you, what number would you split it at? Yep, 0. 0 is definitely the number of choice. It doesn't have to be 0 though, but that's typically what we will choose. Once you do split that up into two separate integrals, then you're ready to write two separate limits. There's some math technicality going on here that non-math people might get a little bit annoyed with how overly technical it is. But it's very important that you understand that these two infinities have nothing to do with each other when you go about solving their limits. You must use a different variable. If you use the same variable within one problem, you're intending that to represent the exact same thing. It is very important that those are different variables because they cannot look at two different infinities in the same manner. No matter how much symmetry you think the graph has, infinity is sneaky and weird and crazy, and it can go at infinitely faster paces if it so desires. And let me tell you that I could change this into a parametric type of form where I could cause one end to head to infinity faster than the other end. And so they cannot be dealt with as the same. Now, for the vertical asymptote issue, if you have an interior vertical asymptote, this one, the bottom is equal to 0 at 1/4. And that's in the interior of 0 to 1. While you get a choice with the negative infinity to infinity split point, here you must split it at that discontinuity. And then you have to create one-sided limits for each of those two. And it's very important that you notice different variables. You must use different variables. Even though you might see that it looks like there's perfect symmetry on both sides of that vertical asymptote, you actually can't view infinity. Here's the beautiful thing. What do these two symbols mean? Do they mean the same number? If every time you write infinity, it's not expressing a particular number, you can't just trust that one infinity and another infinity are alike. You have to be very careful about this issue because infinity is not a variable. It's not a number. It's an understanding of something that we literally can't wrap our arms around. and have to deal with very abstractly. So at this point, you now know how to change all of your improper integrals into limits. Then the other thing is, you get to solve them. Yes! You were hoping you'd get to solve more limits, weren't you? Here we go. There are some new vocabulary words that you are going to become very accustomed to when we hit infinite series. When the limit exists, we say that that improper integral is convergent. If one of the limits of a sum, if any one limit involved is a does not exist, then that improper integral is divergent. And I want to repeat that when you do end up with a situation of two limits that you are solving and then you are adding that sum together, these cannot be combined. These are different letters, can't be brought together. If one of them is a does not exist limit, the sum is off the table. You don't even need to bother with the other one. Both of them have to exist to add them together. So now a little bit of an understanding of what we are actually doing here. If I say that I want to integrate the function 1 over x from 1 to infinity, then the idea is this line, we are looking at area under the curve, starting at 1, and then continuing to move this line further over. I want you to think about this. Can you imagine that there could be an answer to the area when you forever have some little bit under here? It feels like it should keep going. It might continue to grow, but it might not. So I want to remind you of a number that you should have seen already. Do you remember the good old 0.9 repeating? I remember when I was a young child, my brother introduced me to this number, and I argued with him incessantly because I wasn't at an age where I could understand what infinity meant. My argument to why this should not be equal to 1 was no matter how many, there has to be some 0.00000000001 missing. But the idea of infinity is that there isn't. So I can write 0.9, but if I add another 9 on, I have a bigger number. If I add another 9 on, I have a bigger number. I can do this forever. So the idea is you can have this final x coordinate heading to infinity, but your area can have a ceiling on it. Yes, maybe you're adding to the area. In fact, you are. As you move this line over further, you continue to add to the area, and you continue to make that number bigger and bigger. But it is possible that there is a ceiling to that number, and that's what the limits are going to tell us. Do you think I can visually look at this and see whether that is going to be finite or infinite? Eyes are not going to help us. We have to use the math. Now I'm going to do an example of a couple problems in just a second. I want to point out that this is from your textbook. This is what I have already described. The type 1 improper integral You can look at it in your textbook, or you can come back to the video and look at this. I'll also post the notes if you want to look at these. Type 2 and the definition that the textbook gives. So no on it keeps going, on the area being infinite. Anyway, I'm going to keep going. I've got two really important examples to talk to you about and to look at them comparatively. All right. Now, that graph that I just showed you is the graph of 1 over x and looking at 1 to infinity. Let's find out. Is it convergent or divergent? So what I'm going to do is I'm going to replace infinity with a letter. This time I think I'll just put a t in. Now, when I have to deal with an improper integral, I will set up a limit with the integral, but then to the side, I will write the integral as an indefinite integral and just solve it like I would an indefinite integral without limits on it. But right as I would be about to put a plus c on, I bring it back over to the limit. I prefer to do this than to sit around worrying about writing all of this out properly. So I integrate, I get natural log of absolute x. Right there I would put plus c, but instead I'm going to come back over here. And for some of you, you're going to want to just plug in the top minus plug in the bottom, and I'll write that in the next step. You can go ahead and head to that next step. I want to make sure that I'm fully clear on what we are doing, so I'll write it out in more steps. I don't need absolute values because my domain is 1 to infinity. Now I know the natural log of 1 is 0, but what is the natural log of t as t approaches infinity? And I'm going to grab a Desmos graph just to remind you. Yeah. Bringing Desmos over. So here's our logarithm. Does a logarithm continue to go upward as I head to the right? It does. It doesn't look like it would. If I look at it way out to the right, it looks like it flatlined. But it's basically like watching a snail cross the road. It's so slow, you're like, are you going to make it? Are you going to make it? So that means that that area was not bounded. The answer to this limit is infinity, which means that the limit does not exist. And now that further means that the improper integral is divergent. So the official answer is divergent. Let's do another one. Oh, that was my solution ready to go. Okay. Now let's integrate 1 over x squared. 1 over x squared isn't too different from 1 over x, right? Where did my Desmos graph go? So give me 1 second. I'm setting up my Desmos. Okay. Here's the graph of 1 over x squared. And I'm looking at the idea of, again, heading to infinity, getting more and more area under there. But look, if I zoom in enough, I can see that I am continuing to add to the area. And it doesn't matter how far down to the right I go, I can zoom in enough to see that something is being added. The question is it growing bigger and bigger toward a ceiling? So we've got to let the limit decide. I'm going to first write it as a limit. Then to the side, I'm going to look at solving this as an indefinite integral. My integrand is x to the negative 2 power. So I use the power rule. I add 1 to negative 2 and divide by that number. I would be putting a plus c on right now, and I can if I really want to, but it's a waste of time. So I get 1 over x, and that is then coming back over to here. It is important that you write the limit as t approaches infinity in front every time. And do you see what that is? This has a limit of 1. That area does continue to grow as my input heads to infinity, but it grows bigger toward equaling 1, just like how 0.9 adding more 9s causes it to grow, but it is heading to 1, no matter how many 9s I add in. Now, I want to show you, I've got ready to go just looking at the 2 of these just for fun, I suppose. It's kind of interesting if you look at the difference between the 2 areas. But I want to say again, your eyesight cannot be trusted. You cannot eyeball this and say, oh, that's hugging the x-axis much closer than that other function. So obviously, you can't assume that. You could assume if there was an actual area under this blue curve, if there was a limit to that area, do you see that there would be a limit to the area of the red region because it's smaller? But if all you know about this blue area is that it grows to infinity, that's not enough to say that this red area heads to an actual number. You must do the math. Only the limits are going to tell you truly what's happening. Now, the pair of those create an interesting idea that I want you to look into. And I think I had put that in here. Yes, where is it? Hold on. There's no way I'm getting through all these examples, by the way. This right here. This question. In your textbook, this is example 4, and this is worth a look. I'm going to briefly show you the answers, because I need to make sure I spend time going through detailed explanations of how to deal with these problems. But I will tell you that at this moment, if you can put together the limit and the integration ideas that I just talked about, you're ready to just do your homework and you're good to go. But most people need to see examples. This is asking what values of P this is convergent for. We just did 1 over x, and we found out that when P is equal to 1, it diverges. Then we looked at P equaling 2, and we got that that has an area. It is a converging improper integral. But what are the values of P that will diverge versus converge? And it's the integration that tells us. If you look at the only p-value for which this formula is not true is when p is 1. And we looked at that separately. If I use the power rule, assuming that this will never equal 1, it can equal anything else, but p cannot be 1. Then when we go through and integrate, we add 1 to the exponent and divide by that new exponent. And the difference between this limit existing and not existing is all about where is x when the exponent is positive. If p is equal to 1/2, then I'm looking at x to the negative 1/2 plus 1 is positive 1/2. X has a positive exponent. I need to change that to t. Doesn't matter too much, but x has a positive exponent in the numerator. That's going to head to infinity, and it's going to head fast. That definitely diverges. But if p is 3, when I look at what that gives me, x to the power of negative 3 plus 1 is negative 2. That means x has a positive exponent in the denominator. And if I look at the limit as t approaches infinity of this, I'm going to get 0. So what is the border of p to make the difference of whether x shows up as positive exponented in the numerator versus in the denominator? And it's 1. This is something that you want to contemplate right now because it's going to be a big deal when we do infinite series. Contemplate that border issue of that p-value being 1. And notice that if that denominator exponent is greater than 1, you will have an improper integral that converges. But if p is 1 or smaller, it will diverge. Okay, now I'm going back to detailed examples. Oh, and I should probably just show you this. This is their second rule that they provided in the textbook. All right, going back up, and now it's just going to be one example after another time. This problem is going to start by changing this to a limit. I'm going to bring this integral over to the side as an indefinite integral and solve it. Do you see what technique we get to use? Yes. I feel some ultraviolet coming on. If I have a polynomial multiplied by an exponential or a sine or a cosine, the polynomial needs to be the u. The other one will be differentiated or integrated, and the dx needs to go with it. So now, when I take the derivative, I get 1. I don't usually write the middle step in here, but I know when you're starting off with this technique, some people need it. So I'm going to put in a side note. Realize we're taking the derivative of u with respect to x and getting 1, and then multiplying dx to the other side. And then over here, if you need a side note, we are integrating dv and integrating e to the x dx. Integrating v gives me v. Integrating e to the x gives me e to the x. Technically plus c, but we don't worry about the plus c right here when we're doing integration by parts. Then the formula says u times v minus the integral of v du. So that's going to be x times e to the x minus the integral of e to the x times just dx. Whoop it, whoop, whoop. And oh my goodness, we know that. And this is the moment where I would say I was done with that indefinite integral and throw a plus c on. But I'm bringing it back into a definite integral, so I don't want to waste my time with the plus c, and I'm bringing it back over to the limit. When I plug in 0, I get 0 minus e to the 0, which is 1. And then minus, I plug in a. There are way too many negatives involved there. I can, let me make sure that I have the answer here just in case I start messing up on working this. Okay. Yeah. So I have negative 1 minus a e to the a plus e to the a. And I need to limit as a approaches negative infinity. Now, as long as each of these terms has an existing limit, I can break this up into a sum of 3 limits. That's limit laws way back in the day. So when I take the limit with negative 1, I get negative 1 minus. I'm going to write this limit down. And then plus, I'll write this limit down also. So if you think about what the graph of e to the x does when its input is negative infinity, what is the answer to that limit? Zero. But this one, that's my evil laughter for the fact of what your situation is here. If I plug negative infinity into a, I get an infinity times when I plug negative infinity into a for e to the a, that's setting to 0. Do you see it yet? Do you see it? That's indeterminate form. Indeterminate form is best known as 0 over 0 or infinity divided by infinity. But you need to be aware that if an infinity and a 0 are multiplying, that is actually what each of these are, depending on the way you look at it. This one, you could look at it as 0 times 1 over 0. This one, you could look at it as infinity times 1 over infinity. So anytime you have infinity multiplied with 0, you actually have an indeterminate form. You can't solve the limit as is. What are you going to do? Call L'Hopital. When you want to find the limit, L'Hopital, and there's lots of zeros in it, L'Hopital. If you want to find the limit and there's lots of zeros in it, L'Hopital, L'Hopital, L'Hopital. Woo! So, when there's lots of zeros in it, or infinities. So I have run out of room here. I need to lasso this limit. Okay, it's going to give me enough of that to move it over. Move, move, move. Faster. I'm impatient. Faster. That'll be good enough. The first thing I have to do is write this as a fraction. Somebody's got to reciprocate to the denominator. One of them is actually really easy to reciprocate to the denominator. The other one is more complicated. If you change the side of a fraction when you have something that is exponential, negate the exponent, and it's the same exact thing. Hopefully you remember those exponent rules. If you'd chosen the other way, you would wind up in an infinite L'Hopital loop that would be unpleasant because it wouldn't end. Now, I want to make sure that you see, okay, I need to really make this very clear. On an AP exam free response problem, if you need a L'Hopital, you must state the two limits separately. Limit of the numerator, limit of the denominator, not together, separately. You have to write this out. They will not give you credit if you do not write this out, no matter how obvious it is. Now, e to the negative infinity is super infinity. But what's super infinity to infinity? What you want to see is L'Hopital's rule is ready to go if the numerator limit and denominator limit are either both 0 or both infinity. So now I'm going to L'Hopital. Here we go. L'Hopital's rule says the variable is a, because that's the variable of the limit. Derivative of a is 1. Boom, done. In the denominator, you're taking the derivative of e to the negative a. You chain rule and you go e to the shove the baby in, multiply by its derivative, -1. Don't quotient rule when you are L'Hopitalling. You're just taking the derivative of the top, taking the derivative of the bottom. And now let's reassess. I can move this to the numerator if I change it to a positive exponent. And if my input is negative infinity, that's setting to 0. I do want to say, yes, these limits are both does not exist. When you're doing a L'Hopital rule, while the correct answer to the limit is does not exist, when you explain that this is the result that is occurring for that limit, it allows L'Hopital to take place. We have two non-existing limits, but the actual limit we're solving is a ratio of those two. They don't exist isolated from each other within that actual limit. The fact that they're both heading to n infinity, whether positive or negative, means that you can L'Hopital the slopes, the derivatives are the same at that point. Okay. So what does that wind up giving me? We finally get an answer of -1. Now, -1. How could I possibly get an area of -1? Where's my new graph? There it is. Oh, it was e to the x, not -x. There we go. If I look from negative infinity to 0, the curve is completely under the x-axis, so it makes sense that my integral is going to give me a negative answer out. Okay. Time for more good fun. And what time are we at? What time? Your next class starts at 12:55. Okay. I'm going more on that. So I can just watch this one take place. When you have a situation from negative infinity to positive infinity, the first thing is to split it up. And 0 is convenient. Do notice that this function's domain is all real numbers. When I bring the limit in, it's very important that I use different variables. I'll go ahead and do like, hey, let's use the letter H because H has been lonely lately. But I need a different letter for this limit because these are two very different limits within one problem. So let's use k. On the side note, what is the integral of 1 over 1 plus x squared dx as a function? Do you recognize it? It's arctangent. And we'd throw a plus c on. So when I come back over here, arctangent first has 0 plugged in, and then it has h plugged in. And while I'm at it, I'm going to prep the other limit. I plug the k in, minus I plug the 0 in. You have to know how to use unit circle on the AP exam. You have to be able to finish up trig when those are the numbers involved. And, oh, look, it's an arc tank. Ha, ha. Okay, never mind. Most people don't remember the graph of arctangent, but most people do remember the graph of tangent. So let's start there. What does the graph of tangent look like? What's a point that you know it goes through? What's the most famous point that it goes through? Yep, it goes through the origin. It's a function that increases from asymptote to next asymptote. That wasn't the best drawing, but A. It actually has a slope of 1 right about there, so I'm being too picky. Anyway, where are those asymptotes? Where are these two asymptotes? It's important that you know that. Yep, pi over 2. And negative pi over 2. It's also important that you're aware that the inverse tangent as a function only uses this portion of the tangent graph as the inverse. Inverse tangent uses the negative pi over 2 to positive pi over 2, just like sine and just like cosecant. Sine's reciprocal. All of them only use negative to positive pi over 2. So what does that mean inverse tangent looks like? Whee! Look, I've got asymptotes. I'm special. And guess where those asymptotes are? That means if I'm solving for the limit as my input approaches positive infinity, my y value is approaching positive pi over 2. If I'm solving the limit for when x approaches negative infinity, my y value is approaching negative pi over 2. If you're leaving, by the way, you need to make sure you watch the end of the video because I've not gone over all the details, or read your textbook and go through and read the examples. Make sure that you understand correctly everything here. Now, arctangent of 0 is 0. Why am I bothering writing this? What is the answer to this limit? If I'm approaching negative infinity, negative pi over 2. If I'm approaching positive infinity, then this is approaching positive pi over 2, and arctangent of 0 is 0. So I wind up with pi over 2 plus pi over 2. What? The area is pi? The area is pi? Whoa. Whoa. That's so amazing and beautiful. Now, just to let you know, you have 6 minutes before your next class starts. I am going to go over some more examples. And I'm going to keep recording. If you want to not have to watch the recording, stick around a couple minutes and it might just be enough to get you through. The integrand function has a discontinuity at 2. That means I need to replace this endpoint discontinuity with a letter. Pick any letter you feel like. I'll do C this time. And I need to find the limit as C approaches. Take a moment to think about the side. My interval is from 2 to 5. I approach 2 from the right side. Then to the side, I'm going to take the improper integral and solve it. I'm going to show the u substitution quickly. If u is x minus 2, du dx is 1, meaning du is equal to dx. And I have the integral of 1 over root u times du. That's u to the negative 1/2. I can use the power rule, add 1 to the exponent, and multiply by the reciprocal. And then that's square root, put the u back in. And now I go back over to my limit. And I am taking this expression, and I'm first plugging in 5, and then plugging in c and subtracting them. If I think about what is happening as c is a number greater than 2, heading to 2, this is heading to 0, and I have an answer. This improper integral converges, and it converges to 2 root 3. When it comes to your trig functions, you need to be aware of where they have asymptotes. And just to make sure you guys know, it is 12:52 right now. When I need to figure out where a secant's asymptotes are, I think about its reciprocal function. The reciprocal of secant is cosine, and if I graph a nice pretty little cosine, the asymptotes for secant are where it's equal to 0, and it shares the graph at its high and low. So if I'm looking at the interval from 0 to pi over 2, I have an endpoint discontinuity. And I'm approaching pi over 2 from the left side. And the integral of secant is one of those formulas you pretty much have to have memorized. and it's been a while since you've seen it probably. So let me just write out the formula for the integral of secant x is the natural log of the absolute value of secant x plus tangent x. And so I come back over to the limit. I'm assuming if you're here, you don't have a fourth period. Okay, if you have a fourth period, you got to go. I can't keep you from that. I plug in the b, minus I plug in the 0. And then if I look at approaching pi over 2 from the left side, secant is heading to infinity. Secant itself. Wait, I just realized what I did. I messed that up. I was too focused on getting you to your fourth period that I failed to recognize that I integrated, and I need to use that. Whoopsies. Here we go. So I'm plugging in b. And then I'm plugging in 0. And I'm running out of room here, so I've got to squish it. So I've got secant of 0 plus tangent of 0. I need to know what's going on with tangent. So I bring tangent back up. Whee! If tangent is approaching pi over 2 from the left side, tangent is approaching positive infinity. If secant is approaching pi over 2 from the left side, it is also heading to positive infinity. If these were opposite signed infinities, this would be indeterminate. But if you're taking a positive infinity and adding it to another positive infinity, the only thing you're getting is just a bigger infinity than either one of them had. Well, maybe not infinitely bigger, but anyway. You want to realize that this is heading to infinity. So you're looking at the natural log of input heading to infinity, and that's a does not exist. That heads to infinity, so I get to say diverge, and then that's done. And you can also look at your textbook for that. Then I've got a little more. So I want to make sure to talk about an interior discontinuity. This has a discontinuity at x equals 1. I have to first split this up at the discontinuity. Then I need to change these into limits. And if I am between 0 and 1, I'm on the left side of 1. And let's see, 0 to b. And then for this one, I'll use a. And if I am from 1 to 3, I am approaching 1 from the right side. And I might be able to make this a faster ending if I come over to here. The integral of 1 over x minus 1 is the natural log of x minus 1. If I look at just one of those two limits, I'm getting the natural log of heading to 0, and that's negative infinity. So it is divergent, and it's important that you know that you actually do not have to solve the other limit. When you have a sum of two limits that are not using the same variable, if one of them has a does not exist, you can't begin to combine them. The whole thing falls apart, and you don't need to bother with the other limit. Do note the warning. If you did not recognize the discontinuity in the interior, you could have easily wound up with a number, and that would be an error. When you are working on BC integration problems, you have to worry about discontinuities and just be on the lookout for those. And I think that's enough to get through it. You can take a look at this last problem if you like, but I think that's plenty of examples, and you're good to go for your homework, hopefully. And we will spend the next 2 days just reviewing and not learning new stuff.